All right, hey AP Chemistry. This is going to be our Unit 2 lecture part 2. We're going to be talking about bond polarity. So this is an important note about covalent versus ionic compounds. So bonding involves the movement of electrons, valence electrons, whether that movement becomes shared or transferred. So this movement, which we're going to call it ionic character, this is a vocab in AP Chemistry, is dependent on the electronegativity difference, meaning the difference between like subtraction-wise. So like if you needed to know math, right, between the two atoms. Nonpolar covalent bonding would have electrons equally shared. The difference would be small, or for AP, 0. Then you have polar covalent bonding. The difference would be middle, kind of not 0. For AP, we're just going to say 2 non-metals that are different. 2 different non-metals. I'm going to put that in that box here. And then finally, ionic bonding is when we have a large difference in electronegativity. And so there's not going to be some number. It's just going to be very far apart on the periodic table. I will quickly go back and say, look at our table of electronegativities here. I'm going to circle it so you know what I'm talking about, but then I'm going to undo it. Look at this table of electronegativities that we've talked about in the previous lecture. Just remember that order. You're not going to be always given those numbers. If you are, we could use them. If not, remember, whoever is the closest to fluorine is the more electronegative. Okay? All right, so back to this. So there are going to be some AP chemistry tips for talking about molecular or ionic polarity, we'll call it, or ionic bonding and polar and nonpolar covalent bonding. If you Google things or if you look it up or if you go in college, it's a little bit more complex. For AP, they try and make it very specific so it's not vague. The tip for ionic bond or ionic character will say metal and nonmetal, or you're told, like it tells you something's ionic, and it's just a large difference in electronegativity. So of course, that was like a couple things here. Metal, you're told, or a large difference in electronegativity. I'm sorry, that got a little squished up in there. So very simple example, NaCl, MgBr2. These are going to have ionic bonds. There's going to be ionic in character. For polar covalent, the best thing is it's going to be 2 different nonmetals. 2 different nonmetals, and it's going to be having a difference in electronegativity that's not 0. Okay? And so examples are going to be things like HF. The AP exam would probably even consider NO, polar covalent. We could even say CCl, like that bond would be polar, right? So I'm just talking about bonds, okay? And then non-polar covalent, I have 2 tricks for us here. I'm going to try and zoom in so you can see what I'm writing. The 2 tricks are 2 of the same element and all CH bonds. So that is what the AP exam will say that is nonpolar covalent. So if it's 2 of the same elements like Hofbrinkel, those are going to be nonpolar covalent, right? The bond. I'm talking about the bond, not like the whole molecule. That's going to be a different story. But the bond, so like H2, O2. This is what O2 will look like, and we'll draw that later in life. Cl2. Or anything with CH in it. These are all wonderful examples of non-polar covalent bonds. That is just for AP exam or AP chemistry. They kind of just simplify it so we could focus on that. So when we talk about is the bond polar, if it's two of the same elements, no. If it's carbon and hydrogen, no. If it's two different elements, AP would say that it is polar. All right, so there's going to be a specific way we're going to be drawing these polar and non-polar covalent bonds and ionic bonds. I'm going to start with HF, which is polar. Two different elements. So the way that we draw this is we draw an arrow. Here, let's say this is the bond. We draw an arrow. I'm going to draw them in red. We draw an arrow going towards the most electronegative element, and then we draw a vertical line on the least electronegative element. So least electronegative, most electronegative, and we have what's known as a pole. And so the most electronegative element will get like this delta minus. This looks like a weird little Greek symbol. And the least electronegative element will get a delta plus. So this arrow is to represent what's known as a dipole. Pole, like two ends, positive and negative. Delta plus means slightly positive end. And delta minus is slightly negative end. This is only for polar molecules. Nonpolar, watch what we do. For nonpolar, nothing. It is non-polar. That means there are no dipoles. So I don't draw any arrows. I draw nothing. And then finally, for ionic, that is where you just draw like full positive and minus charge, right? What we're going to see is chlorine picks up an electron from sodium here. So gained one electron. That's where the minus charge comes in. And this is lost one electron. That's why it's positive charge there. So that's how you would draw your ionic bonds. You have full positive and negative because they fully gained and lost electrons. For our polar molecules here, I'm going to try and draw a dotted line so I can separate them. For our polar molecules here, we draw poles. We draw an arrow. I'll highlight that again. We draw an arrow. It goes towards the most electronegative element. We draw a vertical line on the least electronegative element, and then we end it. We put the delta minus. Delta is the Greek letter. I'm going to just make a note. Delta, Greek letter. Delta is this thing that looks like this. Looks like a fancy D. It looks like a weird-looking musical note. That's delta minus. On the negative end, that's the most or more electronegative element in the molecule. And then delta plus on the least electronegative end of that molecule. When I say most electronegative, I need more electronegative than other element. Okay? I'm going to skip this guided practice for a moment. I do want to talk about more about bond polarity. Here's a nice little trick. Because all we're going to be given is the periodic table. The further away two elements are from each other on the periodic table, the more polar their bond will be. Right? The further away they are. Right? So looking at HB, I have H and then B. And then I have HN, H and then N. Look, that's further away. H and then O, H and then F. We could clearly see, right? F is more to the right. This is going to be the most polar bond because they're furthest away. This is going to be the least polar bond. I'm not going to say non-polar. It's polar, but there's most and least. And then we have these ones that are in the middle. I would say this is more polar than HN, and that's all I could say. Maybe even less polar than HF, but that's how we're going to do this. That's a nice little trick for us. We only have the periodic table in front of us. The further two elements are from each other on the periodic table, especially if I have a bond that has one of the same element, The further away they are, the more polar they're going to be, right? So even if I did another example, what if I just did like, and we'll see this later. I'm going to erase this, but you know what? Never mind. What if I just did like, if I wanted to compare all of these to, I don't know, NO. NO's looking pretty close. NO might be less polar than HN. And it might be less polar than HB just because they're 1 or 2 away from each other, but NO right next to each other. So we could use the periodic table to help us identify which set of bonds are going to be more or less polar. We can talk about more and less polar bonds. These are for polar covalent bonds. And then, of course, if I did HH, that would actually be the least polar. This is nonpolar. This would be the least polar, of course, because it's nonpolar. So if I had H on itself, there is no separation, no distinction, and so it would be nonpolar. So I wanted to add that into our notes here. It's a nice little trick for us. The further away two elements are from each other on the periodic table, the more polar their bond will be. And so I did that example here. I will end lecture notes by talking about, even though we could have polar bonds, it does not necessarily make the molecule polar. And so on page 6 here, this is the toughest thing for AP chemists, meaning y'all, use. This is the toughest thing for AP chemists. I could have students identify a bond, polar, nonpolar, no problem, but then the moment they look at a molecule, it is the toughest thing. So if you could defeat this, you will be among the strongest to understand this. And we'll talk more about this in class and later. But we'll see that if I have symmetry, that makes a molecule nonpolar. And if I do not have symmetry, if I have asymmetry, that's no symmetry, that will make a molecule polar. But I'm not going to spend too much time on this. This is more on this later. I have wonderful examples here that you could read on your own. For understanding, I want to make sure that you could do the guided practice here. I'm going to get us started on 1 or 2 of them. And then I'd like you to answer the sample problems 1 through 5 here based off of this lecture on bond polarity. So you're going to do the guided practice A through H and sample problems 1 through 5. Now, if you're done with this lecture, you can start getting on the problems. Otherwise, I'm going to get us a little bit guided. If I look at guided practice, it says for each of the bonds listed below, classify each bond as ionic, metallic, polar covalent, or nonpolar covalent. If the bond is ionic, indicate full plus and negative charge. If the bond is polar, indicate partial positive, partial negative. So I'm going to do one of each. So I'll do A again. I'm going to do H, and then I'll do CO. All right, so A, this is metal and nonmetal. We already know that. Metals, hopefully you remember, are on the far left of the periodic table. Nonmetals are on the far right. This means Na is a metal. It's going to be a full positive and full negative. This is ionic. And so that's a little bit of me tugging on your prior knowledge, knowing that metals tend to form positive charge. Nonmetals tend to form negative charge. I'm going to jump over to E. Carbon and oxygen, we have nonmetal and nonmetal. So if that's 2 nonmetals, this is covalent, or what we call molecular. Right? Covalent or molecular is another word. Now the next thing is this polar or nonpolar? If I look at my tricks here, polar is 2 different nonmetals. Boom, done. Carbon and oxygen are 2 different nonmetals. Polar. Done. H and H, this is a metal. This is a metal. So this is just going to be metallic. And I'm not going to talk about polar or nonpolar. Metallics do not get polar or nonpolar. They are just metallic. They have the same electronegativity. They are special. All right, so I'd like you to do the rest. identifying thing. Oh, sorry, I forgot an E. My bad. I forgot an E that I have to add in those poles. So if it's polar and nonpolar, oxygen is more electronegative than carbon. So delta minus, delta plus. Good to go. My bad. I'm sorry there. All right. So get on to doing the rest of the practice problems, do the rest of the guided practice here, and then do sample problems 1 through 5. And that is all for this lecture.